Hi everyone and welcome. In this video, we'll take you step by step through everything you need to get xiRAID Classic up and running on your modern NVMe servers and show you how to integrate it seamlessly with IBM Storage Scale. First, we'll show you our demo architecture so you can see how ordinary x86 hosts with local NVMe drives become a high-performance, highly protected storage platform. Next, we'll introduce xiRAID Classic, its lock-free, AVX accelerated design, and why it's the only RAID engine today to deliver true HA in RAID 5 and RAID 6. Then, we'll walk you through installation on a single host, cover essential configuration options, and reveal advanced tuning techniques to squeeze out every last gigabyte per second. From there, we'll switch to the Xinnor Automation Toolkit to deploy and manage dozens of nodes in one go, before diving into rapid RAID array provisioning, day-to-day management commands, and templated rollouts across your fleet. Finally, we'll install IBM Storage Scale, demonstrate how to resume the process at any stage, and wrap up with file system creation, storage pool and replication policy setup, mounting and performance testing, so you can validate your entire stack from end to end. All right, let's jump in. We will demonstrate how ordinary x86 servers, equipped with local NVMe drives, can be transformed into a high-performance, highly protected storage platform. Modern x86 servers with local PCIe 4, 5, and soon 6 NVMe drives can achieve about 150 gigabytes per second per node when these drives are protected by the high-speed xiRAID Classic RAID 5 engine. IBM Storage Scale then pools these RAID volumes, distributing replicas across two failure groups to provide both node-level and rack-level resilience. The architecture also supports future attachment of disaggregated NVMe fabrics, thanks to the xiRAID Classic engine's flexibility. However, our live demo runs on 10 virtual machines with virtual NVMe drives. While the absolute bandwidth is limited by the hypervisor constraints, the workflow remains identical to a physical deployment. The deployment is orchestrated through a Bastion gateway that drives the automation process. In this setup, Node 1 acts as the master installer, while nodes 1 through 5 form the quorum manager set. Nodes 6 to 9 serve as additional managers, and Node 10 hosts the storage scale GUI. The deployment process follows an automated sequence where xiRAID Classic is first deployed on each virtual machine, followed by the rollout of IBM Storage Scale across the cluster. The odd-numbered nodes are then grouped into Failure Group 101, while the even-numbered nodes are grouped into Failure Group 102. Finally, we create a file system through the GUI with data mirrored across both failure groups. This demonstration proves the architecture's correctness and reliability, even within a resource-constrained virtual environment. Let's continue by learning more about xiRAID Classic. So, what exactly is xiRAID Classic? Think of it as a high-performance, software-defined RAID engine purpose-built for the newest generation of NVMe drives, including those riding on PCI Express 5 today and PCI Express 6 tomorrow. 1. Lock-free data path. Every I/O request moves straight through the pipeline without global locks, eliminating the stalls that plague traditional RAIDs. 2. Smart per core scheduling. xiRAID maps work intelligently across CPU cores, keeping the load perfectly balanced and the latency low even under extreme parallelism. 3. AVX2 acceleration. It leans on AVX2 vector instructions to crunch parity and checksums fast, slashing rebuild times and boosting throughput. 4. Zero cache layers. No writeback, no dirty buffers, no surprises. What you write is what hits the media. 5. In kernel on Linux, the engine runs natively inside the Linux kernel, exposing a standard block device that any application or file system can mount without special drivers. Where does that power really shine? On dense NVMe servers running parallel or clustered file systems. Drop xiRAID Classic underneath, and you get local redundancy with the raw speed those environments demand. And here's the headline feature: true high availability in RAID 5, RAID 6, and beyond. Something no other RAID engine on the market delivered today. That's the foundation. Next up, I'll show you how to install xiRAID Classic and get it humming on your own hardware. All right, Let's start with the most straightforward deployment, installing xiRAID Classic on a single host, following Xenor's official step-by-step guide. Open your browser and head to xenor.io. In the top-level navigation bar, click Resources, then select xiRAID Classic from the drop-down. On the xiRAID Classic Resources page, you'll see a bundle of helpful documents. Before you touch a terminal, pause and review the System Requirements document. It spells out the minimum CPU microarchitecture, supported NVMe controllers, kernel versions, and memory footprints. Double-check that your hardware and Red Hat kernel build line up. It will save you a ton of trouble later. Next, scroll down to the Installation Guide section. You'll notice separate guides for every supported OS flavor. In our case, we need Red Hat Linux. Choose xiRAID Classic, Red Hat Linux Installation Guide. The instruction lists each major release. Find REL 9. Keep the manual open. We'll follow it verbatim in just a moment. First, let's pull in the extra packages xiRAID Classic depends on. Step 1. Enable Red Hat's Code-Ready Builder repository. Step 2. Add the EPEL 9 repository. With Code-Ready Builder and EPEL in place, every library xiRAID Classic needs is now available through DNF. Up next, we'll fetch the xiRAID package bundle and start the actual install. And step 3. Install the kernel headers that match your running kernel. Step 4. Add the official xiRAID repository. Before we can pull the engine itself, we need to teach DNF where to find the signed xiRAID packages and future updates. On some systems, the RPM that adds the xiRAID repository can't be verified. In that case, you'll need to pass NOD-PPG check when installing the repo package. Step 5. Install xiRAID Classic itself, version 4, 3.0. DNF pulls the required kernel module, user space tools, and man pages. With the package installed, let's run a quick 3-point health check to make sure everything landed cleanly. Confirm the kernel module is loaded. Verify the CLI version. Display the license block. On the very first run, the tool presents the end user license agreement. Scroll through and type Yes to accept. Immediately afterward, the command prints your current license status plus a unique hardware key. Make a note of that hardware key. You'll need it when requesting a trial or production license from Xener. All right, friends, the install is done. xiRAID Classic is live. So let's shift gears and dial in the server for peak NVMe performance. If you'd rather fine-tune everything by hand, jump over to the xenor.io blog. We've put together a trio of deep dive posts that walk you through the whole optimization journey, a step-by-step guide to gathering reproducible performance numbers. It covers workload selection, warm-up phases, FEO recipes, and the traps to avoid when testing ultra-fast NVMe arrays. This article drills into BIOS switches, kernel boot flags, IRQ affinity, NUMA pinning, and the must-have packages from EPEL. Follow it to make sure your hardware and OS aren't leaving gigabytes per second on the table. Here we focus on the array itself, stripe size, queue depth, scheduler modes, etc. For every setting, we explain what to change, why it matters, and how it shifts raw, throughput, latency, or rebuild speed. Check them out whenever you're ready to squeeze the absolute maximum from your xiRAID Classic deployment. But what if you're rolling out xiRAID Classic across dozens of servers? Hand installing every box would burn hours, and every keyboard stroke is another chance for typos. That's why we ship the Xenor Automation Toolkit, a fully automated playbook that provisions, configures, and validates each node with a single command. First, it cuts multi-node installs down to size. With just a few clicks, you can push xiRAID Classic to an entire cluster and keep every node perfectly in sync. Second, it bundles a library of performance tuning playbooks. Third, it lets you define a RAID template once, then stamp out identical arrays across dozens of systems in parallel. No more handcrafting configs server by server. Fourth, license management is fully centralized. And finally, if you ever need to roll back, the toolkit can wipe xiRAID clean from multiple machines simultaneously. removing packages, modules, and configs in one shot. In short, the Xinnor Automation Toolkit takes the heavy lifting out of large-scale xiRAID classic deployments, so you can focus on the workloads, not the plumbing. With all prerequisites in place, it's time to fire up the xiRAID toolkit and let it handle the heavy lifting. Launch the toolkit sudo /start.char. Run this script only on your designated master host, the one that already has SSH access to every target server. The toolkit is Ansible-based, so the first thing it does is install or update any helper packages it needs on the master itself. A quick dependency check flashes by, and then the text user interface pops open. Now define your inventory. Firstly, edit server list. The UI opens with just local host pre-configured. Then you can add individual hosts, type in a host name or an IP, and hit enter. You may also add ranges. You can enter CIDR blocks or explicit ranges. The toolkit expands them automatically. And then review. Select Finish to see the complete inventory for a final sanity check. If everything looks right, confirm with OK. Back at the main menu, choose Install xiRAID Classic. If the toolkit detects an older xiRAID package on any host, it offers to remove it first. Approve the cleanup, watch the status bar tick through the uninstall, and then the fresh install begins. Behind the scenes, Ansible pushes the RPMs, loads the kernel module, deploys the user space tools. Progress for every host scrolls in real time, so you always know where things stand. When every task reports OK, the 2i drops you back to the main menu. Installation complete. Should any step fail, a bright red error line appears with the exact task and host name. Fix the issue or ping Xinnor support and rerun the play. The toolkit will pick up right where it left off. That's all it takes to roll out xiRAID Classic to a single box, or to dozens, even hundreds, without breaking a sweat. Once the installation completes, your next stop is licensing. Collect a hardware key from all the nodes and send the keys to Xinnor support. Now let's dive into cluster-wide performance tuning. From the toolkit's main dashboard, simply click Performance Tuning. The wizard auto detects each node's operating system and displays a preview of the tweaks. When the summary looks good, run Toolkit. The engine fans out across the cluster, pushing the optimizations simultaneously. On a 10-node setup, the whole process takes roughly 2 minutes. We've sped up the footage here so you can see the full run. As soon as the last node reports tuning complete, the wizard closes and you're dropped back to the main menu, ready for the next task. Next up, array creation. We'll start on a single host and stick to the command line for maximum clarity. Check the current inventory by typing xiRAID show. Because we haven't configured anything yet, the command returns an empty list, no RAIDs present. Review the create options. xiRAID create-h. The help screen reveals every knob you can turn when spinning up a new array, including RAID name, RAID level, stripe size, and many more. When it comes to squeezing every last ounce of speed out of xiRAID Classic, 3 tuning switches deserve special attention. Enabling the built-in fair queue scheduler to keep I/O handling evenly distributed, even when an application hammers the array from just 1 or 2 CPU cores. Memory pre-allocation. Pre-allocating the parity buffers upfront prevents on-the-fly allocations from stealing CPU cycles under load and lets you cap xiRAID's footprint so the rest of the stack never starves. Dedicated worker cores. Pin xiRAID's worker threads to a specific NUMA local core set. First, let's get a clear view of every block device the OS can see. LSBLK. The list you'll see in our demo lab is full of virtual drives, VDA, VDB, and so on, because we're running inside virtual machines. In a real-world deployment on bare metal, those lines would read dev NVMe 0 and 1, dev NVMe 1 and 1, etc. Now, with the devices identified, we'll spin up a brand new array using the bare-bones command syntax. All we need to specify are the member drives, RAID name and level, xiRAID fills, and sensible defaults for everything else. Although stripe size isn't mandatory, we strongly recommend setting it explicitly to match your drive and workload profile. With the array now defined, let's check its status again with xiRAID show. The command lists our brand new array, along with its key metrics. you'll see the state column reads initializing. That's xiRAID classic filling in parity stripes in the background. Even so, the block device, for example, dev xiRAID, is already online and fully writable. You can go ahead and create a file system, mount it, and start pushing data while the initialization finishes silently behind the scenes. Time to look at day-to-day RAID management. To show a concise inventory, we should run xiRAID show. Our array appears in the list, along with its level, capacity, and current state. To switch to expert view for every tweakable parameter, xiRAID show-e. To configure array parameters, use the xiRAID modify command. Let's view its available options by typing xiRAID modify-h. Next, let's adjust a few parameters on our RAID array. xiRAID modify-n and the array name. And you'll notice we can tweak a wide range of settings. One handy option is request limit, which caps the number of I/O requests the array accepts at once. For this demo, though, we'll focus on CPU affinity. We'll pin xiRAID's I/O handling threads to specific vCPU cores inside our virtual machine, isolating the workload and keeping latency predictable. Now let's list the arrays again. You'll see the updated CPU affinity setting has taken effect. Let's explore additional management options by typing xiRAID-h. The help screen will display the core commands for working with arrays. We can create and delete arrays, adjust their parameters, resize them, change their geometry, import arrays, restore them, and so on. Now let's see how to manage arrays across multiple systems using the same xiRAID Automation Toolkit. Launch the toolkit exactly as we did during the initial installation. Refresh the node list. The dashboard shows every host it can reach. Go ahead and delete the extra local host entry so we're left with only the real cluster nodes. Enter a RAID parameters. Pick the profile that matches your workload. RAID 5, RAID 6. Fill in the basics. Array name. Give the new array an easy-to-spot label. Stripe size, choose the chunk size that best fits your drives. Device list. Enter the NVMe paths, space-separated, that will make up the array. Advanced tuning parameters go into the freeform field below. Type each setting as a simple key value pair. For example, CPU allowed 0. The toolkit pushes these values to every selected node during provisioning. Click OK, and the Automation Toolkit spins up identical xiRAID arrays on all your systems with the specified tuning. No manual SSH, no copy and paste, just a single coordinated rollout. When every task reports OK, the TUI drops you back to the main menu. RAID provisioning complete. To deploy IBM Storage Scale, we've developed a dedicated script that simplifies and accelerates the installation process, while also verifying that everything is set up correctly. The script is divided into stages and runs by default in interactive mode, prompting the user at each step to confirm the status and decide whether to proceed to the next stage. This allows you to start or resume the process from any stage as needed. In addition, the script can also be launched in a non-interactive mode, where it automatically runs from start to finish without user intervention. After installation is complete, the script provides a post-installation health check mode to verify the operational status of the cluster. When launching the script, you can also specify the cluster name as a variable, enabling flexible integration into automated environments. Before running the script, you'll need to adjust several configuration parameters. To do this, open the script in any text editor of your choice. In this example, we'll use Vim. The following fields should be updated: the management IP address, the host names of the nodes where the cluster will be deployed, the node assigned to host the GUI, the device names to be used for NSD creation. Finally, to begin the deployment, simply run the script as the super user. You'll be able to monitor progress and respond to prompts without needing to manually tell the script whether to proceed at each step. The workflow is designed to keep things clear and controlled. Now, I'd like to show you how to launch the script starting from a specific stage. This can be useful if you've already completed part of the setup and want to resume the process from a known point. For example, if the installation was interrupted or you're rerunning a particular section for validation. To do this, simply run the script with the -s parameter followed by the name of the stage you'd like to start from. The installation is now complete. Let's move on to the post-installation health check to verify that everything is working correctly. To do this, run the script again with the HC flag. Now that Storage Scale and the GUI are installed, we can create our first file system graphically. Open a browser, point it to the GUI host, node 10, and log in with the secadmin credentials you created in Phase J. Choose Files, File Systems, Create File System, and set both data and metadata to two-way replication for safety. Select every available NSD. Keep the default placement that already spreads them across failure group 1 with odd nodes and 2 with even nodes. Leave the remaining options unchanged and click Finish. Provisioning takes a couple of minutes. The new file system shows up in the list and quickly changes status to healthy. Refresh the dashboard and you'll see it reported as mounted on all 10 nodes, ready for I/O, fully protected by local xiRAID, and mirrored across the two failure groups. We're ready for a quick performance smoke test. From Bastion, we launch our helper script with the flags perf, fs, and the file system name. The first option starts the I/O workload. The fs flag tells the script which storage scale file system to use. As the benchmark begins, we switch to the GUI and see the real-time performance dashboard to watch throughput. Remember, the demo is running on virtual machines with virtual NVMe devices, so the raw numbers are capped by the hypervisor rather than by xiRAID or storage scale. The script first drives a series of write tests, then automatically flips to the corresponding read passes, logging every result to the console and to the GUI. Even within these limits, you'll see all 10 nodes contributing traffic and the file system remaining in a healthy state, confirming that replication across failure groups and local xiRAID protection add no visible management overhead while the cluster stays fully available under load. And that's how you go from 0 to a fully protected, high-performance xiRAID Classic plus IBM Storage Scale cluster, complete with GUI-driven file system creation and real-time performance validation.